In this lesson, we're going to cover PKI, or Public Key Infrastructure. Spoiler alert, this is a critical piece to securing communications on the internet today. Earlier, we talked about public key cryptography and how it can be used to securely transmit data over an untrusted channel and verify the identity of a sender using digital signatures. PKI is a system that defines the creation, storage, and distribution of digital certificates. A digital certificate is a file that proves that an entity owns a certain public key. A certificate contains information about the public key, the entity it belongs to, and a digital signature from another party that has verified this information. If the signature is valid and we trust the entity that signed the certificate, then we can trust the public key to be used to securely communicate with the entity that owns it. The entity that's responsible for storing, issuing, and signing certificates is referred to as CA, or Certificate Authority. It's a crucial component of a PKI system. There's also an RA, or Registration Authority, that's responsible for verifying the identities of any entities requesting certificates to be signed and stored with the CA. This role is usually lumped together with the CA. A central repository is needed to securely store and index keys, and a certificate management system of some sort makes managing access to stored certificates and issuance of certificates easier. There are a few different types of certificates that have different applications or uses. The one you're probably most familiar with is SSL or TLS Server Certificate. This is a certificate that a web server presents to a client as part of the initial secure setup of an SSL TLS connection. Don't worry, we'll cover SSL TLS in more detail in a future lesson. The client, usually a web browser, will then verify that the subject of the certificate matches the hostname of the server the client is trying to connect to. The client will also verify that the certificate is signed by a certificate authority that the client trusts. It's possible for a certificate to be valid for multiple hostnames. In some cases, a wildcard certificate can be issued, where the hostname is replaced with an asterisk, denoting validity for all hostnames within a domain. It's also possible for a server to use what's called a self-signed certificate. You may have guessed from the name. This certificate has been signed by the same entity that issued the certificate. This would basically be signing your own public key using your private key. Unless you already trusted this key, this certificate would fail to verify. Another certificate type is an SSL TLS client certificate. This is an optional component of SSL TLS connections and is less commonly seen than server certificates. As the name implies, these are certificates that are bound to clients and are used to authenticate the client to the server, allowing access control to an SSL TLS service. These are different from server certificates in that the client certificates aren't issued by a public CA. Usually, the service operator would have their own internal CA, which issues and manages client certificates for their service. There are also code signing certificates, which are used for signing executable programs. This allows users of these signed applications to verify the signatures and ensure that the application was not tampered with. It also lets them verify that the application came from the software author and is not a malicious twin. We've mentioned Certificate Authority Trust, but not really explained it. So let's take some time to go over how it all works. PKI is very much dependent on trust relationships between entities and building a network or chain of trust. This chain of trust has to start somewhere, and that starts with the root certificate authority. These root certificates are self-signed because they're the start of the chain of trust, so there's no higher authority that can sign on their behalf. This root certificate authority can now use the self-signed certificate and the associated private key to begin signing other public keys and issuing certificates. It builds a sort of tree structure with the root private key at the top of the structure. If the root CA signs a certificate and sets a field in the certificate called CA to true, this marks the certificate as an intermediary or subordinate CA. What this means is that the entity that this certificate was issued to can now sign other certificates, and this CA has the same trust as the root CA. An intermediary CA can also sign other intermediate CAs. You can see how this extension of trust from one root CA to intermediaries can begin to build a chain. A certificate that has no authority as a CA is referred to as an end entity or leaf certificate. Similar to a leaf on a tree, it's the end of the tree structure and can be considered the opposite of the roots. You might be wondering how these root CAs wind up being trusted in the first place. Well, that's a very good question. In order to bootstrap this chain of trust, you have to trust a root CA certificate. Otherwise, the whole chain is untrusted. This is done by distributing root CA certificates via alternative channels. Each major OS vendor ships a large number of trusted root CA certificates with their OS, and they typically have their own programs to facilitate distribution of root CA certificates. Most browsers will then utilize the OS-provided store of root certificates. Let's do a deep dive into certificates beyond just their function. The X509 standard is what defines the format of digital certificates. It also defines a certificate revocation list, or CRL, which is a means to distribute a list of certificates that are no longer valid. The X509 standard was first issued in 1988, and the current modern version of the standard is version 3. The fields defined in an X509 certificate are the version, what version of the X509 standard the certificate adheres to, serial number, a unique identifier for their certificate assigned by the CA, which allows the CA to manage and identify individual certificates, certificate signature algorithm. This field indicates what public key algorithm is used for the public key and what hashing algorithm is used to sign the certificate. Issuer name. This field contains information about the authority that signed the certificate. Validity. This contains two subfields, not before and not after, which define the dates when the certificate is valid for. Subject. This field contains identifying information about the entity the certificate was issued to. Subject public key info. These two subfields define the algorithm of the public key, along with the public key itself. Certificate signature algorithm. Same as the subject public key info field, these two fields must match. Certificate signature value, the digital signature data itself. There are also certificate fingerprints, which aren't actually fields in the certificate itself, but are computed by clients when validating or inspecting certificates. These are just hash digests of the whole certificate. You can read about the full X509 standard in the next reading. An alternative to the centralized PKI model of establishing trust and binding identities is what's called the web of trust. A web of trust is where individuals, instead of certificate authorities, sign other individuals' public keys. Before an individual signs a key, they should first verify the person's identity through an agreed-upon mechanism, usually by checking some form of identification, driver's license, passport, etc. Once they've determined the person is who they claim to be, signing their public key is basically vouching for this person. You're saying that you trust that this public key belongs to this individual. This process would be reciprocal, meaning both parties would sign each other's keys. Usually, people who are interested in establishing web of trusts will organize what are called key signing parties, where participants perform the same verification and signing. At the end of the party, everyone's public keys should have been signed by every other participant, establishing a web of trust. In the future, when one of these participants in the initial key signing party establishes trust with a new member, the web of trust extends to include this new member and other individuals they also trust. This allows separate webs of trust to be bridged by individuals and allows the network of trust to grow.